Okay, this is Unit 7, Solutions, Lesson 3. And last time when we met, we talked about Table G solubility curves and how to use that table and answer some questions about different scenarios. So today we're going to continue with our discussion on solutions, and we're going to focus on the nature of the solute and solvent and something that calls like dissolves like. So we're going to revisit bonding for a minute. We're going to talk about temperature, and then we're going to use Table F, which is your solubility guidelines table, to determine whether or not a precipitate is formed in a chemical reaction. So why do some things dissolve and others do not? Well, there is that saying that like dissolves like. And when we talk about that, we have to think about polarity and what type of substances we're dealing with. So what that means is nonpolar will only dissolve nonpolar. So if I take something that's nonpolar and put it in another nonpolar solvent, then it will dissolve or be soluble. If I try to take something that's nonpolar and put it in a polar solvent, then it won't dissolve. And a good example of this is oil and water, because we know that oil is nonpolar. It's also a liquid, and so it can be considered the solute because we're putting one thing in another, and the water is the solvent, so this would be insoluble. Polar will dissolve polar. So I can take water and I can put it in vinegar. So polar dissolves polar. But polar cannot go in nonpolar. And remember, when we talk about polar substances, let's look at water really quickly. We know that water has a dipole moment. We know that this side's slightly positive, this side's slightly negative, because the electrons pull in this direction. So our dipole moment is toward the oxygen because it has a higher electronegativity. So you have that temporary positive negative charge on the molecule. So when we think about ionic, when we think about NaCl, we know that when NaCl bond, it's an ionic bond, and we know that we have this positive and negative charge. We've also talked about when we put salt in water, what happens. The sodium is attracted to the oxygen side because opposites attract, and the chlorine's attracted to the hydrogen side. So it should make sense that an ionic solute will dissolve in a polar solvent because that's our salt in our water. But it will not dissolve in nonpolar. So basically, to sum this all up, nonpolar only dissolves nonpolar. End of story. Polar dissolves polar and ionic. So it doesn't matter what they are talking to you about on an exam, on a Regents exam. If it says naphthalene won't dissolve in water, why? You don't have to know what naphthalene is. I just told you it won't dissolve in water. So water is polar, therefore naphthalene isn't polar and it isn't ionic. So that does not have that like dissolves like scenario going on. So it doesn't matter what substance they give you. If they tell you two things won't dissolve, it's because one is polar and one isn't. If they tell you two things dissolve, it's because they have like polarities. They're either both nonpolar or they're both polar, or one's polar and one's ionic. And we'll do some examples of that in class. I'm going to save this for class, the styrofoam demonstration that shows you water and styrofoam and acetone and styrofoam. So we'll come back to that in class tomorrow. Temperature. What do we know about temperature? Well, for solids, as temp increases, we know that the solubility increases. And we see that on Table G. We also know that for most gases, as temp increases, solubility decreases. And remember that gases have a negative slope, right? Negative slope, and solids have a positive slope. And we've talked about soda. If you have a glass of soda in the refrigerator and a glass of soda on the counter, the one in the refrigerator is going to keep the carbon dioxide in it longer than the one on the counter, because warmer temperatures, gas molecules spread out and it comes out of solution. Pressure. For solid or liquid solutes, gas isn't going to have an effect. I'm just going to put little to no effect. For gases dissolved in liquids, as pressure increases, we know that the solubility will increase. So as pressure increases, solubility increases, and what happens is that the volume also decreases because you're pushing the gas molecules closer together. Recall, we can change the volume of gases. Gas is forced into less space per liquid, so it dissolves more, and that's how they get carbon dioxide into water. When they get the carbon dioxide into soda using pressure, as soon as you open the can, you hear that whoosh, and that's because you're decreasing the pressure. The gas molecules spread out and they come out of solution. Alright, lastly we're going to talk about Table F. It tells you what substances are soluble or insoluble. It is used to predict whether or not a precipitate will form when two ionic solutions are mixed and undergo a double replacement reaction. Remember, double replacement is AB plus CD yields AD plus CB. A precipitate equals insoluble. So think what happens when you put lemon juice in milk and you get those chunks and the curdles. That's kind of what a precipitate is. Maybe not that dramatic, but comes out of solution and is on the bottom. So let's look at Table F. First we're going to look at the soluble side. Ions that form soluble compounds versus ions that form insoluble compounds. What this means is anytime you have a group 1 ion, ammonium nitrate, acetate, hydrogen carbonate, and chlorate, no matter what they combine with, they are always going to be soluble. Okay? There are no exceptions. Now, if I have something that is a halide, group 17, like chlorine, bromine, or iodine, they will be soluble unless they happen to combine with Ag, Pb2+, or Hg2+. So if I have a result of a chemical reaction that forms AgCl, I see Ag here as an exception. So what that means, normally chlorine's going to be soluble. See, it's soluble? But because it combined with Ag, it is going to be insoluble. So this means it's going to form a solid or precipitate. Sulfates. So if I have Na2SO4, I see sulfates here are soluble unless they combine with silver, calcium, strontium, barium, or lead. Well, sodium's not one of the exceptions, so this would be aqueous. That would be soluble. But if I were to have CaSO4, this appears as an exception, so it would be insoluble or solid. Now this side of the table's the opposite. All of these, carbonate, chromate, phosphate, sulfide, and hydroxide, form insoluble compounds. That means they're going to form a precipitate unless they combine with one of the exceptions. So if I have CaCO3, I see that CO3 is on the insoluble side. It combined with calcium. Well, calcium is not in group 1, it's in group 2, and it's not ammonium. So this would be a solid, because remember, these are all insoluble. However, if I formed NH4 2CO3, here's my carbonate, but ammonium's an exception, therefore this will be aqueous. Okay, let's just finish up with a couple of examples and then I have a quick video. So you can read through these directions. I just went through these with you. Let's look at KNO3 and CaCO3. So we're going to go back over here, KNO3. So we know that nitrates, NO3, are always soluble and there's no exceptions. So this is going to be aqueous. And I actually just did CaCO3. I didn't realize that that was the example. But CO3 is on the insoluble side and calcium is not an exception. And we have MgSO4 and ammonium hydroxide. So MgSO4. Here are my sulfates. Sulfates are soluble unless they combine with silver, calcium, strontium, barium, and lead. So that's not an exception, so this would be aqueous. And then ammonium hydroxide. Here's my hydroxide. It's on the insoluble side. Unless I combine with group 1, calcium, barium, strontium, or ammonium. There's my ammonium, it's my exception, so this is going to be soluble. Okay, so the last thing I want to do is finish up with a little video when we were talking about like dissolves like and how we know if something's going to dissolve. So in this example, I'm adding the salt to the water. The water acts as the solvent, so that's what's doing the dissolving, and the salt is the solute. And this is what I showed you before. The water is polar, so the Cl is attracted to the H side of the molecule, and the oxygens are attracted to the Na side of the molecule. As the water molecules surround each ion, a hydration shell is formed around them. This prevents the sodium and chlorine ions from reforming into an ionic compound. So remember, like dissolves like. Polar dissolves polar and ionic, and nonpolar only dissolves nonpolar. Okay, see you tomorrow.